this conformal factor. Ah, okay. I guess the recording only started now. That's fine. So this conformal factor can be singular at singularities, that's to be expected, but it's also singular at horizons and at asymptotic boundaries. So you have to be careful if you use this gauge, if you're interested in features such as horizons and asymptotic behavior. More pragmatically, this gauge is not always convenient. Just if you want to solve the field equations, it's generally easier to use Eddington-Finkelstein gauge. And physically, the main caveat I want to highlight is that you may need to fix some of the non-proper gauge transformations to achieve conformal gauge. So if you're not familiar with what this means, I'll explain this a little bit in my talk, even though I will not go very much into detail. But for the time being, it's sufficient to say that there is a loss of generality in going into conformal gauge. You may lose physical degrees of freedom that are localized at the boundary if you impose this gauge from the very beginning. So quite generally, you have to be careful with gauge fixing, and you have to be particularly careful with gauge fixing if you're interested in boundary states. And in a theory that is as simple as 1 + 1 dimensional gravity, you are mostly interested in boundary states. So that's particularly important to not omit anything that you may want to describe as part of your physical phase space. Okay, so much for the positive aspects. Here are some negative aspects of 1 + 1 dimensions. There is no transverse traceless part in the fluctuations of the metric. So you can decompose any metric fluctuation, which in 2 + 1 in 2 dimensions has 3 independent components, into a gauge part and a trace part. And in general, there would also be a transverse traceless piece, but in two dimensions, that's already all. So if your ambition is to describe a theory of gravity that also has local excitations like gravitational waves, you shouldn't go to 1 + 1 dimensions. No matter how complicated your theory is going to be in 1 + 1 dimensions, it will never describe gravitons. For this, you need at least 2 + 1 dimensions. And the other downside of 1 + 1 dimension is that there are no equations of motion that come from the Einstein-Hilbert action. Indeed, the Einstein equations hold trivially for any 2-dimensional metric. So this is just an off-shell identity that is true for any 2-dimensional metric, regardless of what kind of field equations it may or may not obey. And one way of phrasing this issue is by counting the number of graviton polarizations. So if you do this, you find in d dimensions d times d minus 3/2 independent graviton polarizations. So in 4 dimensions, that would be the well-known 2 helicities, the plus and cross polarizations of gravitational waves. In 3 dimensions, you would get 0. But if you insert 2 dimensions, you get a meaningless -1. Of course, negative number of physical degrees of freedom doesn't make sense. But if phrased in this way, this problem suggests its own solution. Namely, you have to add a degree of freedom in order to get a theory that has at least 0 degrees of freedom, like gravity in 3 dimensions. So the solution is to add a scalar degree of freedom, and this leads then to dilaton gravity. So this is now the bulk action of power counting renormalizable 2-dimensional dilaton gravity. So that action depends functionally on the metric and on the scalar field. This scalar field I denote by x, and I call it dilaton. There's a coupling constant, the 2-dimensional Newton's constant, which will not play an important role in my talk. And then there's always a term where you couple this scalar field, the dilaton, to the Ricci scalar, and I'll always assume coupling of the form x times r. So by field redefinitions, you can always achieve this. And then the remaining input is the specification of 2 functions. So the first function is the kinetic potential u of x that couples to this dx² term, and the second function is the dilaton self-interaction v of x. And by specifying these 2 functions, you specify your specific model. And as you can see already from this action here, you have infinitely many different possibilities of defining such models. So there's not just one theory of 2-dimensional dilaton gravity, there are infinitely many of them. All of them have common features. So in particular, all of them have 0 local physical degrees of freedom. So this naive counting, -1 + 1 is 0, actually works in this case, but of course you should show it by an honest canonical analysis, and you can do this. It's straightforward to do so. So this theory is similar to 3-dimensional gravity in the sense that it has no local physical degrees of freedom, but that doesn't mean that the theory is trivial. You still get solutions with non-trivial global structure, and in particular, you can have non-trivial boundary degrees of freedom. All solutions are known globally for all models. And the question that I want to address now is, what is the most general two-dimensional dilaton gravity model? And by this, I mean a pure gravitational dilaton gravity model. So I don't mean a generalization where you add matter. This you can always do. You can always add any amount of scalar fields or Dirac fermions as you like. But here, I just want to elaborate on theories of that kind. And I want to ask the question, what's the most general version of this action? So can I write down something more general that is perhaps not power counting renormalizable? And if so, what is the most general thing? Now, before doing this, let me show you a list of selected models. I'm not going through the whole list because that will take some time. This is just to point out that specific choices for U and V were made in the literature. And the Suggestive model, as you can see, is a particular simple choice of potentials. The kinetic potential vanishes in that case, and the self-interaction potential is linear. So this is a remarkably simple and yet rich model of two-dimensional dilaton gravity. But the numerous other ones, and depending on how you choose the functions, you get either black holes in de Sitter and anti de Sitter, asymptotically flat, or even arbitrary asymptotics. Good. So let me now address the first question. What is the most general two-dimensional dilaton gravity model? So I'll give you a proof idea how we showed what is the most general such theory. So the proof idea works as follows. We start with the Suggestive model in the metric formulation as our simple starting point. Then we reformulate the Suggestive model as a gauge theory, because this is technically very useful. And then we construct the most general consistent deformation of this gauge theory. I'm going to explain in a bit more detail what this means, but morally what it means is you want to deform your gauge symmetries in such a way that you don't change the number of field degrees of freedom, and you also don't change the number of gauge degrees of freedom, so you maintain the number of physical degrees of freedom. So in our case, it will remain exactly 0, but the way the symmetries act will be different, and thereby you can construct models that are different from Suggestive. Then we impose the restriction that the model is actually a gravity theory. So we could deform the Suggestive model into some gauge theory that has no gravity interpretation. That's not what we're interested in. So we want to have the additional property that the model has an interpretation as a gravitational theory. And finally, we translate back to the metric formulation and then just write down the second order action and interpret it. Okay, so this was the proof idea, and let me now show you how the proof works in a bit more detail. So the first item was to start with the Suggestive model in the metric formulation. So here it is. This is again a bulk action, now specified to the potentials used in the Suggestive case. And as you can see, this dilaton field acts now a bit like a Lagrange multiplier. So if you vary it with respect to, if you vary the action with respect to x, you just get the equation of motion I is equal to lambda, which is constant. So lambda is some constant that you fix. The solutions are then locally de Sitter, anti de Sitter, Minkowski, depending on the sign of lambda. Okay. The second step was to reformulate that model as a gauge theory. So how does this work? Well, it works as follows. So first we go to the Cartan formulation. So instead of metric and dilaton, the action depends now on the dualized spin connection, omega, on the Zweibein, EA, again on a dilaton field X, and additionally on Lagrange multipliers for the torsion constraint. So this action, with some coupling constant that now I call K, has this form here. So the first term is just the curvature 2 form times the dilaton. So this is like the first order version of the X times R term in the metric formulation. Then we have the torsion 2 form TA multiplied by this Lagrange multipliers XA. And then we have the volume form times the potential for Suggestive, which was linear in X. And indeed, you get Palatini-like equation of motion in the sense that even though the spin connection is independent from the Zweibein, after you vary with respect to all fields, you get a set of equations of motion that include vanishing torsion as part of it. So that means that on shell, the connection actually just becomes the Levi-Civita connection, and it is dependent on the Zweibein on shell, which is, very much what happens in the Palatini formulation of Einstein gravity in higher dimensions. And well, so far I've just written down the Cartan formulation of the Suggestive model, but now the important realization is that this is equivalent to a specific gauge theory, namely a non-abelian BF theory. So I can just rewrite the same action in the first line here in this compact form, where x are coadjoint scalars. This denotes the invariant bilinear form on this SL2 gauge algebra. And F is the non-abelian field strength. So F is the A plus A which A, and A is a non-abelian connection that consists of the dual spin connection and the Zweibein. So you can decompose A into omega times the generated J. J generates boosts, and EA times PA. PA generates translations. And in the case of Chekif-Teitelbaum, the algebra that is formed by J and P is just an SL2R algebra, which is isomorphic to SO1,2 or SO2,1. So this gives the de Sitter or anti-de Sitter algebra in 2 dimensions. So here I've written down this algebra. So the commutator between 2 translations gives you the cosmology constant times an epsilon, and the commutator between translations boosts commutes into translations as usual. All right. So this is the gauge theoretic formulation of the Chekif-Teitelbaum model. And now we're interested in the most general consistent deformation of this gauge theory. So I use consistent deformation in the sense of Barnich and Leno. So this goes back to BSD analysis or antifield formalism and analysis of the so-called master equation that was done prominently in the early 90s. So I don't want to introduce all this formalism here. So if you're familiar with BSD formulation, then this should ring some bells. If you're unfamiliar with it, then don't worry, but you can have a look at the original work by Glenn and Mark from '93 if you care about the details. So you start with a free action, I naught, that depends on some fields phi I, and some gauge symmetries are generated by R naught Ji. So that works in this way. So the gauge transformation of the fields is given by this R0 Ji times epsilon I. This can be operators that act on this epsilon J's, and epsilons are the parameters that generate the gauge transformation. And the action is invariant, meaning that the gauge variation of the action should be 0. So delta I with respect to the fields times this gauge transformation has to vanish. And then you deform the action. So you can do this with some formal deformation parameter and formal power series in this deformation parameter. We can do this non-perturbative, it doesn't matter. But yeah, expressed in terms of this deformation parameter, this works as follows. So you have your original action, and then you deform it by a term I1, linear in lambda, a term I2, quadratic in lambda, and in principle arbitrary higher order terms. And you do a similar deformation of your gauge symmetries. But you maintain the number of field degrees of freedom, so you don't change the number of the phi i's. And you also have to make sure that you don't add or subtract gauge symmetries. So you want to make sure that you have the same dimension of your physical phase space before and after the deformation. So this is what consistent refers to. Consistent deformations maintain the number of field and gauge degrees of freedom. And again, technically what you do is you deform the master equation and then solve the so-called descent equations, but I'm not going into these details here. Okay, so what does this mean in our context? Our starting point is a BF action, which I've slightly rewritten. So I've expanded this again in terms of these coadjoint scalars, which I now call xi, and the connection, which I call ai. And here I've written down the structure constants of SL2 times this x case. So this is again equivalent to the Cartan formulation that I've shown earlier. It's just repackaged here. And the gauge symmetries are non-abelian, so they act in the usual way on the connection. So you have the usual abelian term here, and here you have the non-abelian term with the structure constants of SL2. And also the coadjoint scalars transform with the same structure constants. Okay, so this is a starting point. Now we're interested in the most general consistent deformation of the BF action. And the answer is that it's given by a so-called Poisson-Sigma model. So if you compare these two lines, what is the difference? Well, the difference is only this term here. So here I have a general Poisson tensor, Pij, that can depend arbitrarily on this x case. So above here, the dependence had to be linear. Here, the dependence can be nonlinear. That's the main difference. And this quantity has to obey some properties. So it's a Poisson tensor, so that means it's antisymmetric. So Pij is minus Pji. And it has to obey these Jacobi identities. So these are nonlinear identities that constrain this Poisson tensor. Okay, And the gauge symmetries are then also deformed. So instead of the linear gauge symmetries above here, you have now in general nonlinear gauge symmetries, at least if the Poisson tensor is nonlinear in the xi's. So this second term that above here contained the structure constants now contains arbitrary structure functions. And also the x's transform into something that is in general nonlinear. And well, this was developed in the early 90s by Ikeda and independently Schall and Strobel. And Izawa showed the proof that the most general consistent deformation of the BF action is actually a Poisson sigma model. And that's the result that we're using. So now we have answered what is the most general consistent deformation of the Chakif-Teitelbaum model in the gauge theoretic formulation. But we still want to impose that the deformed model is a gravity theory. So what do we mean by that? Well, we want to make sure that the field content has a gravity interpretation. So X should still be a scalar field that we may want to call dilaton. And the connection still should decompose into a spin connection and a Zweibein. And here I'm using now.
Question, I think, yeah.
Yeah, sure, please.
Yeah, Emine, go ahead.
So in the previous slide, so I don't know if this question makes sense, but why this P generalized structure constant, well, structure coefficient, why does it have to only depend on X but not A's? What happens if you...
Sure. No, that wouldn't work because A is a one form and X a scalar field. So you want to make sure that your action is a two form, meaning you can integrate over it. So you can only have terms of the form D AI, like the first term here, or you can have a term of the form AI wedge AJ, but you cannot have higher powers of A appearing because this is a form degree. So the only thing that can appear non-linearly or even non-polynomial are the scalar fields xk.
But can't you construct some scalar from the A's?
No, unless you add additional structure, which is what you don't want to do in the context of consistent deformations. So of course, if you introduce something like a Hodge star, then you have another one form available, namely star AI, and then you could contract this with AI, and then you can construct scalars. But that introduces additional structure that we didn't have originally, and that goes beyond the realm of consistent deformations. It would no longer be a topological field theory of Schwarz type if we introduce a Hodge star. So with the field content and the available structure, this is really the most general thing that you can have.
Okay, thank you.
Sure. But thanks for the question. It did make sense. It was not so trivial. Okay, so yes.
Yeah, then we have another question.
Sure.
Yeah, Umut, go ahead.
Hi, Daniel, Umut here.
Hi, Umut.
Yeah, I have a question. So about this level looking thing K, that doesn't have to be a level, I think, at this point. Because yeah, in the original action, in the JT action, you had you just said
1 over G2. Yes.
Yeah, 1 over G2, and the other parameter you had was lambda, but here.
No, okay. So yeah, thanks for the question. I'm going to address it on the last slide of this proof, but I can say it now already. So I'm just using K because it's a more common notation in the gauge theory context, and you're right to suspect that it may have something to do with a level, like in Chern-Simons theories in one dimension higher. But in the gravity context, K is really just 1 over Newton's constant. So you can think of K, well, up to factors of 4 or so, as 1 over G2. And the other parameter, that was just a property of the Chakif-Teitelbaum model, that there was this parameter lambda, and that you should think of as being part of the Poisson tensor. So this Poisson tensor depends arbitrarily on this, on the scalar fields xk, but there could be additional parameters that you sprinkle into the Poisson tensor. So yeah, the functions of xk that appear as components of the Poisson tensor could contain additional coupling constants like this lambda in the Chakif-Teitelbaum model.
Yeah. Okay. Thank you. And this K, is there any requirement on the?
You mean some quantization condition or something?
Yeah. If you want to embed this in string theory, for example.
There may be quantization conditions especially in Euclidean signature, based on similar arguments as for Chern-Simons, that under large gauge transformations you want to make sure that your action, transforms by a suitable integer multiple of 2 pi I.
Okay.
But in Lorentzian signature, and in general, I don't know if there's going to be a generic requirement that K has to be in some rational set. But you're right that in string theory context, K typically is constrained to be in some rational set. It doesn't have to be integers, but yeah.
What I had in mind was just not necessarily string theory, but if you just write the gravitational path integral using this theory, as you said, like, and then you impose on the the gauge. So the action is invariant under gauge transformations, but there may be large gauge transformations which require K to be a.
You're right, and that may indeed be the case, but yeah, that's a bit, I think, harder to analyze in full generality, and that was, as far as I know, only analyzed for those models that have an interpretation in terms of non-abelian gauge symmetries. Because there it's straightforward to understand also what is the group structure. But in this more general case, even though we know the algebra precisely, because we know how infinitesimally transformations work, it's harder to make statements about the nonlinear version of these gauge symmetries. So therefore, yeah, I don't know what the general statement is. It's an interesting question, I think, but it's an open one.
Okay, thanks.
Okay, so yeah, so let me come back to the restriction I want to impose. So I want to impose that the model is a gravity theory, not just some Poisson sigma model. So apart from the field content, my main requirement is that the gauge symmetries correspond onshore to diffeomorphisms and local Lorentz transformations. And we implemented this in this recent work with Romain Rossicone and Céline Zwickel just less than 2 months ago. So what does this mean in terms of the Poisson tensor? Well, it implies that the Poisson tensor is not an arbitrary Poisson tensor. First of all, it has to be a 3 times 3 matrix just because we want this field content. Second, because of local Lorentz invariance, we must make sure that the first row and column is linear in the target space coordinates. Remember that I mentioned that the gauge symmetries, standard Yang-Mills type of gauge symmetries, if the Poisson tensor is linear. So there's always going to be some standard gauge symmetries part of our theory if we require local Lorentz transformations, because, well, that's always of Yang-Mills type. So therefore, the local Lorentz transformations require that this part remains linear. But this remaining entry in the Poisson tensor is in principle, at least at this stage, an arbitrary function of all 3 scalar fields, x plus, and x minus. And because of antisymmetry, that's all you can have. So you only have 3 independent entries. Now, it turns out that this is not all there is to this story. So the Jacobi identities impose a further restriction. So this function v is not arbitrary. It has to be constrained to be a function of only 2 arguments. And it's physically plausible why this is the case. So basically, instead of depending arbitrarily on x and xa, it has to depend on x and on the contraction of xa with xa. So on a Lorentz invariant combination of these Lagrange multipliers of the torsion constraints. But then there are no further restrictions. So this is now the most general Poisson tensor that you can have that has a gravity interpretation. So this now answers the question, what is the most general consistent deformation of Chekif-Teitelbaum that has a gravity interpretation? In the first order formulation, it's given by this action here, and you can see it's very similar to Chekif-Teitelbaum. So these 2 terms are identical to what we had in Chekif-Teitelbaum. But the term that was proportional to the volume form now changes. So instead of the linear term that we had for Chekif-Teitelbaum, where we had lambda times x, now we have an arbitrary function, not just of x, but of x and of the Lorentz invariant combination xa. So here's some special cases that are well known. Chekif-Teitelbaum, as I mentioned, is just v is lambda times x. The CJGS model is another famous model. It's very simple. There v is just a constant. And the power counting renormalizable models that I mentioned earlier, they are obtained if you choose v in this specific form. So you have a bilinear term in xa, so xa times the kinetic function u of x, and then you have the self-interaction function v of x. And with this, you can show that the corresponding second order action is the class of power counting renormalizable models. Okay, so to show you what this implies in the metric formulation, let's just translate back, which is straightforward. So we eliminate the spin connection and the Lagrange multiplier for torsion constraints. through their own equations of motion, and we obtain the metric from the Zweibein in the usual way. And then we replace, okay, sorry, here I call it kappa. So I replaced K by essentially 1 over Newton's constant. And this is now the second order action that we get. So again, we have some coupling constant. We have this coupling between dilaton and Ritchie scalar in some canonical form. And the main change is now, instead of a kinetic and a self-induction potential, we have an arbitrary potential of 2 arguments. The first argument is the dilaton field, and the second argument is like a kinetic term for the dilaton, so it's dx squared. And it can be an arbitrary function thereof. Now, this action was rediscovered a number of times. It's also known as kinetic gravity braiding or Hondesky theory. But until recently, I think it's fair to say there were no good or interesting models that went beyond the class of power counting renormalizable models. So yeah, this is what I just said. So the goals for the remainder of the talk is first to describe some generic features that are common to all these models. As I'll show you, you can treat these models all on equal footing and write down just what is the most general solution to the field equations for all of them. And then in the last part of the talk, I want to propose an intriguing new family of models that goes beyond the class of power counting renormalizable models and that has interesting physical features that I want to highlight. Okay, so let me still stay general and discuss generic aspects of all models.
Daniel, we have a question.
Sure, sure.
Yeah, Emine, go ahead.
Sorry, you hear me?
Yes.
Yeah.
So what happens if you want to repeat this steps for 2+1 dimensions? Like, can you write down the most
yes.
general theory?
Yes, you can. Of course, it depends there what your starting point is. There are different three-dimensional gravity theories that are not just different in the sense of, you know, making different choices for U and V in dilaton gravity, but that are different in terms of the number of physical degrees of freedom. So if you start with Einstein gravity, then if you follow this line, you find out it's actually rigid in the following sense. So when you translate Einstein gravity in 3 dimensions into the gauge theoretic formulation, you find it's a Chern-Simons theory. And then you can use the result that is also known in the literature, and I think it's also contained in the work by Glenn and Mark, that the most general consistent deformation of Chern-Simons theory is another Chern-Simons theory. So if you want your Chern-Simons theory still to be interpretable as a gravity theory, you have to make sure that, you know, the field content is again the spin connection and the Zweibein. And then it turns out, well, the only essential deformation you can make is you can change the value of the cosmology constant, so it can be positive, negative, or 0. But apart from that, you cannot make any additional changes. That would be the analog statement that is technically very similar to the statement I just made in 1+1 dimensions. If you're asking about more general theories of gravity, I mean, there are theories of gravity in 3 dimensions that also have degrees of freedom, like massive gravity theories, and there's a whole slew of them. And then you would have to redo this analysis, and that's a bit more complicated because you don't have a formulation as a pure gauge theory. You have more complicated Chern-Simons-like theories that, however, do have local physical degrees of freedom. And there, as far as I know, the question is not answered, what is the most general deformation? But it's a good question to ask, and probably it's answerable, but I don't know what the answer is, and I think it's not known what the answer is for massive gravity theories.
Okay, thank you.
Sure. Good. So the first thing I want to discuss is all classical solutions for all models. And there are up to 2 sectors of these solutions. The first are the so-called constant dilaton vacuum. These are solutions where the dilaton is constant and it has to solve this non-differential equation. So x plus and x minus have to vanish. And
Daniel, we have one more question.
Sorry. Yeah, sure. Please.
Yeah, Utku, go ahead.
Thank you. I have a question about this most general model. Yes, in here. Can we obtain this model from the higher dimensional model, for instance, 4 dimension with this constraints on this Poisson tensor. I mean, we can obtain this from four-dimensional gravity plus some fields, Maxwell plus dilaton, etc. But with this constraint on this Poisson tensor.
Yes, so that is possible. So I mean, in this talk, I'm taking an intrinsic 1 + 1 dimensional perspective, but it's true that many models in 1 + 1 dimensions can be obtained by dimensional reduction of higher dimensional theories of gravity. So that includes, well, maybe let me briefly show you again the list of models. So that includes in this 8th line here, what I call spherically reduced gravity is just Einstein gravity in n dimensions. But then you do a dimensional reduction on a n-2 sphere, and you end up with a specific 1 + 1 dimensional dilaton gravity model of that type. And not all models in 1 + 1 dimensions have an interpretation in terms of higher dimensions, but well, some of them do. And as Shaheen Chakchabari was asking, I guess 1 hour ago or so, is it possible to obtain this most general two-dimensional classes of this model here with higher derivative terms by dimensionally reducing higher dimensional Hondesky theory? And I can repeat my answer here. I think the answer is yes, but this hasn't been done yet. So if you want to have an example of a model that is not power counting renormalizable, but that still emerges from dimensional reduction of higher dimensional gravity theory, you have to go beyond Einstein gravity. You have to take some higher derivative theory like Hondesky theory. But yeah, this was not investigated yet, so I can't give you a more detailed answer.
By the way, it is this model. Do you have any restriction on this potential, for instance, scale invariance or conformal invariance? Or
no, at this stage, I don't have any restriction on the potential whatsoever. So this is really the most general theory, and you can pick any. I mean, in principle, you can pick any function of these two arguments that you like. Of course, not every one of them will be physically interesting or meaningful. Some of them might have curvature singularities at infinity or something like that. But yeah, in principle, you're completely free to choose any function of these two arguments that you like.
Thank you very much. All
right, good. So let me finally conclude the constant dilaton vacuum. They're not very interesting to start with. All solutions in the sector are maximally symmetric, so they're either de Sitter, anti-de Sitter, or Minkowski. And such solutions may not even exist because, well, again, let me show briefly, where was it? The CGHS model. So in the CGHS model, V is equal to lambda, and lambda is a non-zero constant. So the equation lambda is equal to 0 just won't have any solution for X because it's X independent. So these solutions don't have to exist for a given model. And even if they exist, you need an infinite fine-tuning of the dilaton field. So, and okay, even if you care about the solutions, they're very simple. So there's not much to be discussed. Okay, so therefore, let me instead focus on the other sector, the so-called linear dilaton vacuum. They always exist, and they are less trivial than the constant dilaton vacuum. And you can use the dilaton as a sort of radial coordinate. And here's the solution for all models. Given now in Eddington-Finkelstein gauge for convenience, because then it's easier to obtain these solutions explicitly. So V is advanced time coordinate, X is this radial coordinate, and simultaneously the dilaton field. And Q and W are two functions that are known explicitly in integral form. So if you give me a potential curly V, I can write down Q and W in terms of integrals of this V with some known kernel. And that means when you integrate these equations, you get integration constants. And there's one essential integration constant, one constant of motion, which are denoted by M. And physically, this has the interpretation as mass of the solution. So that's important to point out that all solutions are labeled by this constant of motion. And in those cases where these models make physical sense, this constant of motion has the significance of the mass of your solution. All right, I mean, we know the results explicitly and you can find them in the paper, so I refer to this for details, but I'll not display them here because, yeah, they're not so illuminating, I think. Good. Now that we have the most general solution for the metric, we can also consider thermodynamical observables. So the Hawking-Unruh temperature immediately follows from surface gravity, so it follows from the metric. And the entropy follows from our general form of the action. So you can use, for instance, Wald's method, or you can use the Euclidean path integral formulation. And the result that you get is that the entropy up to the coupling constant is just given by the dilaton evaluated at the black hole horizon. So this is the generic result. It is true for all dilaton gravity models, regardless of the choice of the potential. And the mass then follows from the first law. And other thermodynamical quantities are derivable as well, like the specific heat. I'm going to be a bit more explicit when I discuss a specific class of examples. So for power counting renormalized models, results are known explicitly. This was done already more than a decade ago in this paper with Bob McNeese. And for the generic models, well, results are known in principle, but it still needs to be worked out explicitly in full generality. So there's still work to be done in the near future for generic models. Okay, and the last set of statements I want to mention here in full generality concerns the physical phase space and the boundary charges. So locally, we have 0 physical degrees of freedom in these models, but there can be boundary degrees of freedom or edge states, and that means these models are tailor-made for holographic applications. And not just conceptually, also technically, they're very similar to Chern-Simons theories in 3 dimensions. So in some sense, these Poisson-Sigma models are the 2-dimensional analog of Chern-Simons theories. Now, the key aspect that is true in this context is that boundary conditions are crucial, and they can lead to non-proper gauge transformations. So non-proper gauge transformations, in the second line here, are gauge transformations that preserve the boundary conditions, but that change the physical state. So for instance, gauge parameters that are of order unity in the asymptotic region. And proper gauge transformations are the usual ones that preserve boundary conditions and the physical state. So in other words, proper gauge transformations remain pure gauge at the boundary, but non-proper gauge transformations, they are no longer gauge transformations at the boundary. They act in a non-trivial way on the physical state. And well, I'm not going to introduce this formalism in detail here, but for the purpose of this talk, it's sufficient to say that the key quantities that characterize whether or not the gauge transformation is proper or non-proper are the so-called boundary charges. So the variation is given by some operator that acts on the transformation parameters epsilon, and it depends on the fields and the variations. So epsilon is the parameter of the gauge transformation that preserve our boundary conditions. Phi are the phase space or field variables. Delta phi are the variations allowed by the boundary conditions. Always some operator that is known explicitly for any given model. And for proper gauge transformations, this expression vanishes. That is what defines the gauge transformation to be proper. And for non-propers, gauge transformation is non-zero. And in our context, the expression is very simple and explicit. So the result for the boundary charges in the first order formulation is just given by the gauge parameters contracted with the variation of these scalar fields xi. And this is again true for all models and for all boundary conditions. So it's again a very universal result. You can translate this into the second order, into the metric formulation. The result is also known explicitly. It's a bit longer, but you can find the expression in the paper with Romain and Céline. Yeah, so this concludes what I wanted to say in full generality. And I see I have, well, about 12 minutes left. So let me use these 12 minutes for the last remaining goal of this talk, namely to present in more detail a specific class of new examples. But if there are questions at this point, please don't hesitate to interrupt me. Okay, so the last part of my talk, I want to discuss dilaton scale invariant models. It's a specific model family that we investigated. So these are potentials where V is chosen in the following way. So instead of having a function of 2 arguments, we have a function of 1 argument. So it's x times this function u that depends on x tilde, and x tilde is the ratio of dx squared over x squared. And why this choice? Well, there is some scaling symmetry if you make this choice. So if you rescale x to lambda times x, x tilde is scale invariant. So the potential transforms into the potential times lambda. And since also the other term, x times r, is linear in x and therefore has a factor lambda, the action just gets rescaled by lambda. So this is not a symmetry of the action, but it is a symmetry of the equations of motion. And we just impose this because that leads to explicit results for the for the metric, and also because it's nice to have a sort of reduction of the model space to something more concrete. And indeed, we made a further simplification. So instead of considering generic functions u, we assumed now that this is a second order polynomial. So we have in our potential one term that is linear in x, like for Chekhov-Teitelbaum, one term that is linear in the x squared. So it's the x squared over x, like in the Witten black hole. And then the non-trivial new ingredient, going beyond the power counting renormalizable class of models, is this term proportional to A2, which is the x to the 4 divided by x cubed. So if A2 and A1 vanishes, then we're back to Chekhov-Teitelbaum. But instead, we're going to assume that A2 is non-zero, because otherwise we're back to known models. So we want to have some genuine new model that has a higher derivative terms, and therefore we assume A2 is non-zero. Okay, and it turns out that these models are well, classifiable in terms of a discriminant delta, which is a bilinear combination of these three constants, A0, A1, and A2. And I'm going to focus on the positive delta case. The other cases are described in the paper as well, but this is the most interesting one. And it's, well, good to introduce suggestive notation. So we are going to relabel and restrict the parameters suitably. So I'm introducing Z and W. Z is just the square root of this discriminant minus 1, and W is just a shifted version of A1. And we're imposing this convexity condition so that absolute value of W is bounded. And what this leads to is to solutions that have intriguing geometries. So solutions that are subjected to these constraints lead to Penrose diagrams of this form. So the richest scalar is infinite at infinite dilaton. Sorry, the richest scalar at infinite dilaton is a negative constant. So we asymptote to ADS2, like in Chekhov-Teitelbaum. L here is just the ADS radius. But at vanishing dilaton, the richest scalar asymptotes to a positive constant. Because of these inequalities, you can check that, yeah, the combination of these constants is always positive, so therefore this is a positive number. So what this means is that solutions to these models asymptote or smoothly interpolate between an asymptotic ADS2 and the Sitter interior of the black hole. So the red region is the black hole region. So it means we have black holes in ADS2 that in the far future interpolate to the Sitter space. And that's kind of intriguing. Okay, so that's one intriguing property of these models. The other is evidence for Lifshitz behavior. So what is Lifshitz behavior? By Lifshitz behavior, I mean anisotropic scale invariance of this form. So t goes to lambda to the z times t and x to lambda times x. And z is the anisotropic Lifshitz exponent. If z is 1, we're back to the isotropic case, but in general, z is not equal to 1. And it's generated by a Killing vector of this type. And I mean, this has found many applications, particularly in holography and quantum critical systems at the Lifshitz point. So it's kind of curious that this pops up automatically in our models. And if you look at the thermodynamical behavior, so the relation between
Daniel,
entropy.
We have two questions actually.
Yeah, sure, please.
Yeah, Umut, go ahead. Yeah.
Hi, Daniel. Yeah, so
Hi.
About the Penrose diagram you showed in the previous slide.
Yes.
I'm trying to understand this. So you have an ADS, but is there there should be a cosmological horizon as well, right? So is it future infinity?
No, there's only one horizon. There's only one horizon. What
happens to the Sitter horizon?
Well, if you want it is, there's no independent de Sitter horizon. I don't want to say it has merged with the black hole horizon, because that suggests it's an extremal horizon, which is not the case. So there is just a single horizon in these models. Here the richest scalar is positive, but in between it decreases. So it's not constant, it's just asymptotically constant. And then the sign changes at some point, and the sign change can happen either outside the horizon, or it can happen inside the horizon. Or exactly on the horizon if you fine tune. well, we investigated actually this issue in a bit more detail. So there's no way that you can interpret the horizon as a approximate de Sitter horizon, because for this, you would need that the Ritchie scalar doesn't change too much in the vicinity of the horizon. And we can prove that, at least if we're in this family of models, it's always true that the Ritchie scalar changes appreciably precisely in the region around the horizon. So there's never a good approximation where this horizon is approximately de Sitter. Okay. So the de Sitter region is really just in the very far future. So it's always localized in the inside of the Penrose diagram.
Okay, yeah, nice.
Yeah, we have one more question.
Sure.
Utku, go ahead.
Thank you very much. I have a question about this ADS2, DS2 interpolation.
Yes.
Do we have some kind of critical temperature in this case? So, I mean, do we have some thermodynamical explanation to this property? Do we have critical temperature and?
No. So there is no critical temperature. There is no phase transition. There's no Hawking page-like phase transition. The specific heat remains always positive, at least for positive set. So there's no way that you have a transition between a phase where you might just be ADS everywhere or de Sitter everywhere, or there's also not a phase transition to a phase where you don't have a black hole. So it's not like, say in the BTZ black hole, or more generally in black holes in ADS, that you have a Hawking page phase transition where you have, depending on the temperature, either the black hole is the dominant saddle point or thermal ADS is the dominant saddle point. Here it's always the black hole who is the dominant saddle point.
Thank you very much.
Sure. Okay, yeah, so regarding this Lifshitz-like behavior, so what we found is that the entropy scales like the mass as follows. So entropy is mass to the power 1 over Z plus 1. And this is well known for Lifshitz theories. So this was discussed in these papers here by González Troncoso and Edgar Shagulian. And you can think of this formula as a generalization of the Cardy formula. So if Z is equal to 1, this would be essentially the Cardy formula. Entropy scales like the square root of the mass. This is one way to phrase the Cardy formula. And for Lifshitz theories, this is the generalization. So if Z is not equal to 1, you have this specific power of mass in the scaling. So entropy is m to 1 over Z plus 1. And this is exactly what we find. So this is an independent evidence of Lifshitz-like behavior. And indeed, if we look at the ground state, we find as part of our killing vectors precisely that killing vector that generates this anisotropic scale invariant. So that's yet another piece of evidence that there is some Lifshitz-like behavior in our model. Okay, sorry. That statement above here was for Lifshitz-like field theories, and this is the statement that we find the following relation between entropy and mass for our black hole solution, so the two coincide. But let me point out that from a dual quantum field theory perspective, if there is one, this is a bit puzzling because, I mean, there's just not enough space to understand where this anisotropic Lifshitz scaling behavior should come from. I mean, in higher dimensions, you can understand it as an anisotropic scaling between different coordinates. But here we're in 1 plus 1 dimension, so the boundary just as a time dimension. So it's a bit puzzling, and I'm not sure what it means from a dual quantum field theory perspective, or if there's a dual quantum field theory perspective. But still, I find the evidence for Lifshitz scaling behavior non-trivial because of this thermodynamic relationship. And that's usually a good guideline. I mean, if your entropy tells you something, usually you have to take it seriously. Okay, so there are different ranges of the Lifshitz anisotropy parameter, depending on which the model behaves very differently. Let me go just briefly through this because I think in 1 minute my official time is over. So if Z is negative, then the asymptotic value of the Ritchie scalar is negative. At R naught, it's positive. The specific heat has a negative sign, and the entropy would diverge as temperature goes to 0. So these are not perhaps very physical models. If Z is equal to 0, we're in a special case where we have asymptotically flat solutions and the specific heat actually diverges. And for positive Z smaller than 1, we always get the same behavior of specific heat and signs of Ricci scalars for positive set. What differs is the behavior of entropy as temperature goes to 0. So for set equals 1, it goes exactly linearly. But for sets more than 1, it goes to 0 faster than linearly, and for set bigger than 1, slower than linearly. And for very large set, it even behaves like order unity if you take the large set limit. Okay, and there are a couple of special cases that we studied explicitly. So for set equals 1, you recover not just qualitatively, but also quantitatively the well-known cardiology. So you can write the entropy in this cardi-like form with a specific central charge that is determined by the coupling constant and this parameter W. And you also find that the mass parameter transforms with the expected infinitesimal Schwarzian derivative, where psi is now a leading order parameter function in the boundary preserving diffeomorphisms. The other case that we investigated in a bit more detail is the large set limit. And the reason for doing so is because the Ricci scalar behaves very curiously, namely it approaches a step function. So here we plotted the Ricci scalar for, not an infinite value of z, but z equals to 500. And you see that, well, it's very close to a step function. And this is the dilaton here is given in units of the horizon value. So you see that the transition happens exactly at the horizon. So this goes back to the question that Ummus was asking. So from this, you can also see that even at large set, the region around the horizon is precisely the region where it's not a good approximation to assume that the Ricci scalar is constant. So it's not an approximately de Sitter region. But if you're slightly inside, then you're quickly transiting to de Sitter if Z is very large. And if you're slightly outside, you have a quick transit to anti-de Sitter. So yeah, so this is the result that we get, which means there's a sharp transition from ADS2 to DS2 at the horizon. And the steep gradients that you get near the horizon are reminiscent of the large dimension expansion that was studied extensively by Roberto Emperon and collaborators in the past decade. So it's actually very suggestive for future work to use 1/z as a small expansion parameter and to get some mileage out of that. This is something that we intend to do at some point in the future. But yeah, we haven't done so, but it's very suggestive that this should give you a similar benefit as the large dimension expansion used in general relativity. Okay, so yeah, I'm not sure what we should do. Since my time is officially over, I can either skip to the last slide or I can go on. So I leave this up to the chairman.
We can give actually 5 minutes more if you need.
Yeah, I mean, but I don't want to sort of spam you with technical details. But okay,
okay.
It's maybe let me see. Yeah, I mean, is any okay? Maybe let me just. So this is maybe more directed towards experts. So let me be brief on this. And if you don't understand the vocabulary I'm using, then just bear with me for a minute. So. We imposed specific boundary conditions and studied asymptotic symmetries for a specific case, namely for the isotropic case. We have a more or less standard Pfeffer-Gram expansion for the metric. So if you are familiar with any aspect of ADS-CFD, you must have seen this. The slightly unusual assumption concerns the dilaton. So the dilaton is allowed to fluctuate to leading order, which is not what is always done in this context. And it turns out that these boundary conditions are preserved by asymptotic killing vectors that have this specific form. And assuming a disk topology, we get a specific asymptotic killing vector algebra. And the technical highlight I want to mention here is that the charges associated with these asymptotic symmetries are not integrable in field space if you assume that psi and eta, the leading order terms in these asymptotic killing vectors, are state independent, which seems a natural assumption. However, if you allow for specific state dependence of these parameters psi and eta, then the charges actually become integrable, which makes sense because non-integrable charges usually have to do with fluxes, and since we don't have local degrees of freedom, there shouldn't be any gravitational waves, so there's no reason for the charges to be not integrable. And indeed, by allowing suitable state dependence, you can make the charges integrable. And then, well, for a specific choice that we made, you find charges in a very simple form that form just the Heisenberg algebra. So that's as simple as it gets. as it gets. The symmetries in this case are just Heisenberg symmetries. All right, so yeah, this was the last technical comment that I wanted to make, and let me just give you a brief summary. So this is the takeaway bulk action. So the most general two-dimensional dilaton gravity model up to addition of matter is given by this action with an arbitrary function of two arguments, one of which is the dilaton and the other is the dx squared. So this provides a huge playground for model building, or at least for toy model building. Generic aspects are universally applicable. So the solution space is explicitly known for all these models. We have expressions for the charges, but still some results need to be worked out. For instance, holographic normalization, so the addition of suitable boundary counter terms to this action, specifically in the case of fluctuating dilaton boundary conditions, this is something that still needs to be worked out in full generality. And then we focused on a specific class of examples, just because we found by actually accident that this has this intriguing geometric behavior of interpolating between ante de sitter and de sitter. And there are numerous intriguing loose ends that I think deserve further study in the future. So the short summary of my talk is that generalized dilaton gravity in 2 dimensions provides numerous research avenues for the future. And here's a selected to-do list. Maybe I'll just add these remarks without going into detail. So if you have questions about some of those, let me just present them here and let them here for a minute for you to read. What I think could be interesting, maybe let me just highlight 3 things besides things that I said already, like the large set limit. So it would be interesting to find these Schwarzian type of boundary actions that govern the boundary degrees of freedom for generic models of 2-dimensional dilaton gravity. This hasn't been achieved yet. It has only been achieved for isolated cases. It would be interesting to add matter and to study back reactions and black hole evaporation. And there you could probably beneficially exploit the large set limit. And it would be interesting to come back to the question I mentioned on the very first slide, namely how generous holography by, going beyond ADS-CFD. So we did already a couple of first steps by proposing a model of flat space holography and by taking some limits like Newton-Cartan and Carolian limits. But I think there's much more to be explored, and yeah, I think this is interesting work for the near future. So again, in summary, there are exciting new possibilities that are provided by generalized dilaton gravity in 2 dimensions. And at this point, let me thank you for attention. And before I let you ask further questions, let me just finally point out that we will have Strings 2022 in Vienna, July 18 to 22. And it will take place as an in-person event, even though right now the COVID numbers are again rising, but extrapolating from the past years, numbers should be fine again by July. And yeah, you find further information on the conference webpage. So I hope to see some of you in Vienna next July, and let me stop here and thank you for your attention again, and you can ask questions now. Thanks.
Yeah, thanks Daniel for such a nice actually talk. So do you have time to receive questions or?
I'm fine if people still want to ask questions.
Okay, well, let us receive a couple of them. Is there any question or comments? Utku?
I was raised my hands before, but maybe I can ask a very basic question. Since we don't have some kind of, as I understand, some kind of in the BF formulation Lie symmetry. I mean, in BF formulation, if I had some underlying symmetry Lie algebra, I can construct this as a BF theory, yes. And then I can immediately supersymmetrize this. As I understand, in this context, since we don't have some kind of Lie algebra symmetry, so I cannot say something about this supersymmetric version of this generalized action, right?
Oh, no, you can. So thanks for that question. So I didn't address supersymmetry. Of course, that's another generalization that you could envisage. And actually, I'm sorry of not having put it on this list here. But there, I think a lot of the statements are already known. even though some things still may be worthwhile working out in detail. So let me make the statement first. You can still exploit the same tools. So you can formulate two-dimensional supergravity as a graded Poisson sigma model. So the difference is now that you have a larger set of scalar fields, and that some of them will be now anti-commuting. So you have sort of supersymmetric partners of the dilaton. You have a dilatino, and that leads to additional constraints on the Poisson tensor. But again, there will be some arbitrary function that you can choose according to your wish. And this deformation procedure also works in the graded case. So if you want to start not with a BF theory, but with a graded BF theory, so say you start with the supersymmetric version of the Chekif-Teitelbaum model, then instead of SL2, you start with the corresponding superalgebra, and then you get a graded BF theory, and then you can follow the same logic, and the end result will be a graded Poisson sigma model. And then you just have to impose your restrictions that, this graded Poisson sigma model is not just some random graded gauge theory, but it is actually a supergravity theory. So again, you get additional restrictions like local Lorentz invariance that constrain your Poisson tensor. And yeah, then you will get a generalization of or an extension of the result that I presented to the supersymmetric case. But this wasn't written up yet. I'm just explaining in words how it can be done, and that I think it's straightforward to be done, but it wasn't done yet. And it might be actually interesting to just, sit down and do it. I don't think it's going to be complicated, although maybe there's some hidden complications that I'm not aware of at the moment. But yeah, I think it should be straightforward to generalize this to the supersymmetric case. And in this case, the fact that you have nonlinear symmetries is not I mean, that doesn't prevent you from doing this. Oh, okay. So you're right that you have non-abelian, I mean, non-linear gauge symmetries. So it's a generalization of the standard abelian or graded abelian. Sorry, not abelian, of the Lie case. So instead of a graded Lie algebra, you get something that probably you can call a graded Lie algebroid. I mean, there's the mathematical structure behind the gauge symmetries of Poisson sigma models you can understand in terms of so-called Lie algebroids. I didn't want to, use this vocabulary, but now that you're asking, let me mention it. And yeah, and the supersymmetric version of this Lie algebroids would then describe the most general theory of 1 + 1 dimensional supergravity.
Thank you very much.
Yeah, Umut has a question. Yeah.
Well, about the first item on your outlook, the SYK-like correspondences. Have you tried to understand what happens if you? I mean, what do you do to the SYK model?
Yeah, no, I have not understood this. So I mean, I put it on the first place just because SYK features, of course, prominently in the past half decade. I think, for me at least, a reasonable way to approach this is by first addressing the second item, because one of the crucial links in the SYK correspondence between the gravity side and the field theory side is the realization that you get the Schwarz in action as an effective action, for your Goldstone modes on the field theory side, and as the action that governs the edge states or the boundary gravitons on the gravity side. So I think to make progress, it could be important to understand how these Schwarz type of boundary actions work in generic two-dimensional dilaton gravity. And we've not succeeded in achieving this yet.
Yeah, I'm asking this because I'm trying to see, for example, if you can do this perturbatively. Like, I mean, if you can perturbatively deform your JT gravity, does it make sense to ask this question even? And then try to see what that would correspond to in the SYK model. Some small deformation which you can expand around.
Yeah, I mean, this is true, but it's tricky. So you can do a small deformation in the sense that you have a small deformation parameter, and if that deformation parameter goes to 0, you're back to Chekif-Teitelbaum. That's fine. The problem is that even if you have a small deformation parameter, the effect that it has on geometry can still be huge. I mean, so what I mean is, you might have a small deformation parameter, but it may lead to models that are no longer asymptotically ADS, but they are asymptotically, I don't know, singular or asymptotically flat or asymptotically something.
What I really, I understand. But what I really meant is that, for example, you had this this potential V, right? So you had A0, A1, A2, these parameters.
Yes,
you can take A1 and A2 to be small, for example, and you can try to understand maybe those terms as some operators you turn on in the SYK model. Some you know, like the sources for high operators or something like that.
I agree. I think that might be a productive way to think about it. Yeah, we haven't thought about it yet in more detail. I mean, beyond of what you see, but I think that might be a fruitful way of approaching it. I agree. But yeah, sadly, I cannot offer more insights at this stage. So
well, you already offered a lot, so thanks. So, but well, another question I have is about this torsion that you turned off at the beginning, because I guess you were trying to get something close to Einstein gravity. Or is there another reason for that? I was trying to understand what happens if you try to generalize to a torsionful case.
Okay, so I didn't go into these details, but okay, since you're asking, let me take the opportunity. So actually, so when I say this is the most general theory of gravity, I mean, of course, up to possible reformulations. So let's look at this most general action here. If I present it in this Cartan form, you will actually see that it's no longer true that torsion vanishes onshore. Why? Well, because if I vary with respect to the XA, I no longer get TA is equal to 0, but instead I get TA is, well, proportional to the volume form times the derivative of V with respect to XA. So whenever this potential does depend on XA, in this first order form, torsion is not going to be 0. So if you want, you can reformulate these models as an f of R and f of T theory, or f of R and T theories, where R means curvature and T means scalar invariant constructed from the torsion. So this is an equivalent reformulation of the same theory, but it, I guess, has a slightly different emphasis. So indeed, if you were to write down the most general, scalar invariant that you can construct out of curvature and torsion in 2 dimension, it would be equivalent to that action upon integrating in field degrees of freedom. So in the simplest case, suppose that the action is just an f of R theory, then you can convert this into dilaton gravity just by integrating in the dilaton field, basically. So you have instead x times R plus volume form times some function of x. And if you choose the function of x suitably, you reproduce the corresponding f of R theory. And the same remark applies to when you include torsion as well. So adding torsion doesn't add anything new. That's what I want to say. Or in the first order formulation, it's already added automatically.
Yeah, thanks.
Yeah, Daniel, it seems there's no more question. So
okay,
we can stop here. Daniel, thanks again for having time for this talk. Yeah, we can.
Thanks for inviting me, and thanks for all the questions. And see you.
Yeah.
At some
See
point.
you.
Bye bye.
Bye. Take care.